Hello, my name is Frank Rubicki, and in this presentation I'm going to share my research that I have currently conducted in biosensor development. The scope of my undergraduate senior thesis was to fabricate a 3D microfluidic paper-based analytical device using a slip chip to screen for C-reactive protein, or CRP. This project uses sandwich ELISA with necessary reagents stored in the paper device such that this device could be used outside the clinical setting for point-of-care testing. To build this sensor, I decided to use a standard screen printing kit. Wax printers are the gold standard for constructing well-defined hydrophobic barriers in paper, but I was unable to access a wax printer and followed literature to find an alternative methodology. Unfortunately, I was unable to successfully print the hydrophobic ink through the paper. This picture shows a simple colored solution spreading outside the designated confines of the hydrophobic well. This forced me to change the scope of my project from my original 3D slip chip to an immunodot assay. The red, green, blue, or RGB mean intensity output of the CRP control was compared to every reference standard using z-score evaluation to generate p-values for the CRP ELISA immunodot procedure. Each CRP standard generated a statistically greater RGB colorimetric output than the control. To improve possible future clinical applications, a calibration curve is needed to correlate RGB intensity with CRP concentration. The results indicate a fair agreement between RGB colorimetric intensity and the CRP standards. However, it is somewhat disconcerting that the error bars from the 2 nanogram sample, the 0.5 nanogram sample, and the 0.25 nanogram sample are not within the best fit slope. The calibration curve has a considerable amount of room for improvement before this assay could be used in a clinical setting for quantitative screening. To determine the colorimetric output cutoff for false positive and false negative tests, and to determine the quality of the plot versus the control, specifically if a certain CRP standard should be used in the calibration curve, a receiver operator characteristic curve was generated to detect the diagnostic ability of the ELISA immunodot in response to a changing discrimination threshold. The receiver operator characteristic curve derived from combining all CRP standards had an area under the curve of 0.88, indicating a borderline outstanding test. The RGB output discrimination threshold was selected as 81.427, and from this value, the sensitivity was 91.8% and the specificity was 96.5%. This past June, I was hired by the Sankusei lab to work on a point-of-care lateral flow device used to detect microRNA indicated in patients with suspected post-traumatic stress disorder using an electrochemical platform. The first goal of this project has been to create and optimize a screen-printed electrode. I have made this electrode design in GIMP photo editing software and screen-printed conductive carbon paste for the working and counter electrodes, and a silver chloride paste for the reference electrode. This design fabrication requires functionalizing the working electrode through diazolization and EDC-NHS coupling, which can be seen to the right. For a proof of concept experiment, cortisol antibodies were immobilized onto the working electrode surface. I am currently working on characterizing the screen-printed electrodes. The figure in the top right verifies that the working electrode is being properly immobilized with the diazonium salt during the first LSV scan, due to the peak seen at minus 0.3 volts. The absence of this peak in subsequent scans indicates that the reaction has run to completion. This is important because the diazonium salt is light sensitive, and improper LSV scans likely indicate that the diazonium salt has degraded. In the top left, each of the electrochemical impedance spectroscopy was taken at each step of the immobilization procedure, and the absolute impedance values were calculated using a best fit circuit and can be seen below. These results are promising but still need to be further optimized to prove that the immobilization procedure is following the proper protocol and methodology. One step that I have been working on to better improve the results is to deliver a more smooth working electrode. The figure in the bottom right is an atomic force microscopy 3D image of a small sample of a working electrode surface. The 6 micron deviation in carbon paste is consistent across other electrodes, and hopefully I can reduce this number moving forward. Simultaneously, I've been working on a bubble assay using platinum nanoparticles immobilized to staple and pencil tips. My goal is to quantify the formation of bubbles using impedance spectroscopy on these surfaces. Impedance was selected because the air pockets that the bubbles form are very insulating, and hopefully, impedance spectroscopy can be used to quantify the formation of nanobubbles. I have also selected pencil tips and staples as substrates for the electrodes for testing, because these common items are very inexpensive and highly available, which could potentially make these platforms viable for future mass production. As seen in the top row, these bubbles can be visualized under a microscope. However, the impedance for the experimental platinum nanoparticle group has currently been lower than the control seen in the top right. I have been expecting the opposite result and need to further optimize and reconfigure my experiment to obtain cleaner data that better fits the theory. I hope you enjoyed my digital portfolio, and thank you for taking the time to see my prior research.